Hi class, today we're looking at present value. And you may have some money right now, you might be thinking about setting it aside for investment. Maybe you're thinking about spending it, but if you're looking at an investment, you can go online and find lots of banks or investment institutions, they might be called, that offer interest rates, different packages, different products and services. Here I'm at the Scotiabank website. I just selected this particular bank. Growing up, I had an account at Scotiabank. I remember having GICs. There's lots of different types of GICs, but a guaranteed investment certificate is one where your principal investment is safe. So the present value, what you would invest at the beginning of the term, is safe. You can't lose it even if the interest rates change. But sometimes interest rates can go up. If they vary, you can benefit from that. So there's different products they offer here. The non-redeemable type, where you can't cash it in until the end of the term. But if you're willing to do that, they generally yield a higher return and have different products where if you want to cash it in a little bit early with a penalty, you have to wait up to at least a month. For cashable GIC, they have accelerated type where if you're wanting to roll it back in and reinvest it, you can get a higher interest rate if you're willing to give it to the bank for a longer period of time, and so on. Under the non-redeemable guaranteed investment certificates, we see the overview here. They are safe. The security of the principal is guaranteed. The interest rate is also guaranteed, and you can choose from different rates depending on the length of time you're going to invest. Some of them are what are called registered plans, which means it can be linked to your tax return, and the government can also credit you for investment in a registered plan. If you look at current rates here, you'll see that minimum investments are required to take advantage of more frequent compounding, and as the interest is compounded more often, it benefits the person who's investing. And if we want to invest for monthly compounding, we'd have to be willing to lock it in for a minimum of a year, and as you invest it for longer periods of time, the interest rate goes up. Not that much. GICs have fairly low interest rates. So this is just to give you some idea of some products out there that use compounding interest. And today we're going to be looking at present value. A couple ways I want to represent present value. I'm going to use this scenario here. $10,000 is your goal. You want to have $10,000 accumulated 5 years from now. So that's a future value. You're going to purchase a used car, and you shop around, you get an interest rate of 6% on your investment, and it's compounded annually. And you want to know, what would you need to invest now at present in order to produce that future amount or future value? So we can represent present value and future value relationship in a couple ways. We can start by recalling the compound interest formula, which is that the principal is compounded according to a growth rate 1 plus I, compounded n times. This is geometric growth, or exponential growth for a geometric sequence. Now, present value is our principal, P, and future value is our amount, A. When we look at representing this using a timeline, that's one representation. It's sort of a visual to show what's happening to your money. You start at time 0, which would be now, and then you invest to the end of the 5 years. And you're only making one investment. So your investment here, which is your principal, grows as follows. So you connect your investment to the very end, and sometimes timelines will allow you to track the growth of different investments along the way. When we look at annuities later, we'll be using timelines. According to the calculation, input is the principal times 1 plus I to the 5. In this case, we know the interest rate is 6%, so it'll be 0.06. So we could update that and say it's equal to our present value times 1.06 to the exponent 5. And at the end, we hope to have our $10,000. So the timeline shows both the time on an axis here in years, as well as the dollar value of money. Okay, so this is first way of representing present value, future value. The second way would be to look at how we calculate this, starting with an input P. Very first operation we do to this is to multiply it by 1.06 to the exponent n, or in this case 5, and directly that gives us a. So there's not much math required in calculating that. We have to calculate the interest rate, do BEDMAS, do your exponent first, and then multiply that by our principal or present value. So to solve for P, we would, in this case, if you're given the amount, which in this case would be the $10,000, the reverse of that would be dividing by 1.06 to the 5. So we could calculate this as follows. We'd put in the $10,000 for our future value amount, set that equal to the principal required to generate that, compounded at 6% over 5 annual periods, apply our input-output diagram or arrow diagram, which says take the amount, divide by 1.06 raised to the exponent 5, and that will give us our present value. And I calculate this to the nearest cent is $7,472.58, which is maybe a little bit surprising for some of you, that you only need to invest a little bit less than $7,500 to grow to $10,000 in a 5-year period of time. So you're earning almost $2,500 and some dollars interest, which is quite a good amount for an investment of such a short period of time. Over 30 or 40-year period, if you let that 72 investment sit there, it probably would grow to much larger than $10,000, certainly. So we can remember calculating the interest rate, just as a review, that's simply the difference between the future value and the present value. Okay, now just to go back and look at the key ideas for this lesson, they're summarized as follows. The principal or present value P represents money borrowed or invested at the beginning of the time period. The effect of compounding produces an amount, also called the future value A, at the end of the time period. A timeline we saw visually shows the link between these two quantities, and an input-output or arrow diagram also shows the operations which connect those two variables P and A. So we're filling in those key terms here. Give you time to record those, and then I'm going to continue with the video lesson looking at some technological applications here using the TVM solver of the graphing calculator. Okay, your textbook, 7.3, page 438, you'll find a summary of a method which solves problems, financial problems for us, using an app on the graphing calculator called the TVM, or Time Value of Money Solver. And this is the way it works. There are certain quantities that we need to input. N is the number of years for the investment or the loan. I is the annual interest rate. PV represents the present value. PMT represents the payment, if there is one. FV represents the future value, or what we've also called A. Payments per year represents the number of payments that are made in the investment. If it's a single investment, which is of the type that we've looked at so far, it would be once. And the compounding per year, C/Y, is the compounding frequency, which could be semi-annual 2 times a year, monthly 12 times a year, all the way down to maybe even weekly or daily. Compounding frequency is inputted. And we have some specifics that make this TVM solver work. One of the specifics is the negative or positive nature of values. So negative values are values which have been invested, paid out, and positive values which would be money that is paid back to you. So if you have to give money up to start the investment, you would call that a negative value. So for example, a investment would be money coming back to you in the future, but at present the PV would be less than 0, okay, and the amount would be greater than 0. If it were a loan and you were borrowing or you had purchased something, then that would be perhaps money coming to you right away, where the present value might be positive, and over time it accumulates to a debt that you owe to pay back, in which case the future value would be money that you'd have to pay back for having purchased something or borrowed money. So certain situations might involve positive or negative values, and in the case where we don't know a value, or in many cases it's initially 0, we just enter 0. Enter 0 for a quantity not known, or in some cases not used. And I've duplicated PMT, but PMT usually for future value and present value questions, we don't use the PMT. We'll see that later on. That's more applicable for investments where we're making multiple payments over time. As far as we've looked at, compounding involved a single investment at the beginning of the time period. So we can use this TVM solver to solve some questions, and if we were to repeat the calculation which we did to generate the answer to this scenario, that'll be your first example for having used this, and then we can practice it over time and use it a little bit in the class and also for our final year-end project. Okay, having completed the meanings for each of these key quantities, the number of years, annual rate, our initial principal or present value, PMT only used for annuities, so enter 0 for one-time investments. In that case, enter 1 for payments per year, and compounding per year is simply the frequency. Negative and positive values were explained, as well as the necessity to sometimes use 0 if a value is not known or not used. Now let's go to the TVM solver. We turn on a graphing calculator, clear the screen, go to Apps, Finance. In this case, option number 1 gives us the TVM solver. So in this example, we were looking at a 5-year investment window. So 5 entered in here. The interest rate per year was 6%. It was compounded annually. That'll be indicated down here as compounding per year is 1. Okay, payments per year is 1 for a single investment. The future value we don't know yet, so we'll leave it as 0. The payment we'll leave it as 0 because it's not being used, and we're investing an unknown amount. So actually, let me go back here. Present value is not known. Future value is known. It's 10,000. This is going to come back to us as money into our pocket or into our bank account, so it's going to be a positive value. Now when we go to calculate the principal or present value, we go alpha solve. So that would be the alpha key followed by the enter button, alpha enter, and we get negative 74.7258, which is exactly what we had calculated earlier using the input-output diagram. Okay, let's look at some problems here on your Blackline Master 7-4. This is present value questions, and some of them will ask you to solve for things besides P. In number 3, the future value is given, as well as the present value. So a $2,500 investment growing to $3,000 after 3 years. Certainly it's possible if interest here is compounded semi-annually. We have the compounding frequency, but what would be the interest rate on that investment? Now it's compounded semi-annually, but if we use the TVM solver here, we can go to our question here, pull up our TVM solver, and we can try to solve this one almost by systematic trial. So we're going to put in 3 years for our investment. We have an interest rate which is not known. Our present value would be negative 2,500. Oh, we got an input error there, so let's try this, negative 2,500. Okay, good. So I used subtraction before. Payment leave is 0. The future value, it grows to $3,000. Single payment, so once initially, compounding frequency is 2. And here we can, with the TVM solver, directly determine the interest rate. So here we would go alpha solve, and we get an interest rate of 6.17%. And that's, of course, the annual rate. So no need to calculate the semi-annual rate here, because the TVM solver I% corresponds to the annual rate. So again, systematic trial would have been a slow process. What we would be doing to solve that question would be setting up our known information as we can, using the formula, $2,500 growing to 3,000. Now that sign convention for the TVM solver, don't mistakenly use that in your algebraic solution. So we have future value equals present value, 1 plus I to the n. In this case, the annual rate is not known. So we do know, though, that the term rate is the annual rate divided by 2. Because of the compounding frequency, it's compounded twice per year. N in this case would be twice per year times 3 years. It would be 6 compounding periods, so n is 6. And now we can put in our values. So we have 3,000 equals 2,500. 1 plus I term, which is unknown to us, raised to the exponent 6. We can solve this. 3,000 over 2,500, divide both sides. As remember our input-output diagram, the first step, if we know the amount, but we don't know the present value, would be to divide both sides by 1 plus I to the n. But in this case, what we don't know is the term interest rate. So what I'm doing here is kind of mentally going through the input-output diagram, and I'm doing opposite operations. So off to the side here, if we weren't certain about how to do that, think about it like this. You have your term interest rate. First thing you have to do to it is you have to add 1 to it. Then you're going to take that and you're going to take the result, raise it to the exponent 6. Then you're going to multiply by the principal, and then your result would be the amount. So if you know the amount, first step would be divide by p, which is what I did. Now, what's the opposite of raising something to the exponent 6? Well, it would be raising something to the exponent 1/6. Now, we'll look at exponent laws later on in the course, or maybe we've already looked at it, depending on the order of the units here. But we could also think of it as the opposite of the 6th exponent would be the 6th root. So we could take the 6th root of the previous result, and then finally we would subtract 1, and that would give us term interest rate. So I'm at the point now where I've divided my principal on both sides. Now I have to apply the 6th power, which would be, or 6th root rather, 3,000 over 2,500. That would give me 1 plus I term. Evaluating the 6th root in your calculator is just a matter of finding a button which allows you to enter in the degree of the root. And there's some examples in your textbook which you may have already seen. In section 7.2, they explain how to algebraically use a root, and that's shown on page 432 of your textbook. The keystrokes for most calculators would be quite similar. It's shown there. So here we're going to take the 6th root of both sides and then finally subtract 1 from that result. and that would give us the term rate. And the term rate could be doubled to give us the annual rate. Based on this, we know that the annual rate would be twice the term rate. All right, now I'll mathematically calculate that out, and I'll show you one other way you can solve that. Continuing on here, just showing in steps, the quotient there under the root is 1.2. The sixth root of that is 1.03, and I carry lots of decimal places because this is a financial question. So when I convert this back into a percent, I want a lot of options for my decimal places so that when I round it, it wouldn't introduce too much error in the calculation of the future values. So 3.08% is approximately the term interest rate, and the annual rate would be double that, or about 6.17. Now, looking at solving this by systematic trial would be tedious, but we could try values for the term rate and keep checking. And of course, as a check at this point, what we could do is go in and say, well, we know that the left side of the equation is the amount, and that's $3,000, and the right side is the calculation of P times 1 plus I to the N, where we're using 2,500, and we think that the interest rate for the term is about 3.08%, and that's to the exponent 6 for 3 years at semi-annual with 6 compounding periods. So if we were to calculate that, we get pretty much exactly 3,000, but we're off a little bit in the decimal place, probably because of the rounding here. And that just emphasizes the fact that when we do approximate our interest rate, we're always going to lose, even for a small period of time, 3 years, almost $1. So close enough, left side equals right side, so that therefore I'm convinced that that's the correct annual interest rate. Now, another way we could solve this problem is to take our graphing calculator, and instead of using the TVM solver, which can directly solve it, we could solve this graphically. So what we're going to do here is, one more step needs to be shown. If we were looking at solving 3,000 equals 2,500 times 1 plus some unknown interest rate to the 6, what we could do is consider this to be a function. This is a function, we'll call this y1, and this can be a function y2. And where they're equal, they intersect. So there'd be a point of intersection. Okay. Now, we on the graphing calculator can't represent interest rate I, but we can certainly use x. So what I would do is I'd put in 2,500 1 plus x to the 6 as y2, and then leave y1 as 3,000 as follows. Go to y equals, clear out anything that's there, put in 3,000 as our future value, 2,500 times 1 plus x to the power of 6, and in this case we know the interest rate. If we didn't know it, keep in mind our window needs to be set, and that can be a tricky little thing to do here. So we could at least expect that the interest rate is going to be a number probably much less than even 0.1, and so what I would do here in the window is maybe start at 0 and go to 0.1 by 0.005 maybe. And in the y direction, two functions intersecting. In this case, the y coordinate of the point of intersection is known to be 3,000. So I would probably start at, well, the investment is initially worth $2,500, so let's show maybe 2,400 as the minimum y, and how about 3,100 as the maximum y, and let's increase by, say, even 50 at a time, and graph that. So there's our 3,000 future value line. Here's our 2,500 1 plus x to the 6, and we can see the point of intersection here. If we're to trace and move along there, we can see that the x value is, well, somewhere between 0.03 and 0.04, but much closer to 0.03. Okay, so we can estimate that, or we can simply go to the second calculate or second trace option, try to locate 5 for intersection, identify y1 as the horizontal line, y2 is our second function, and then the guess at the point of intersection here. Graphing calculator will calculate it out, and of course what's limiting my answer here is the number of decimal places that it's showing. So I'm going to repeat that, go to mode and change the digits to floating, and then as I regraph that I can go second trace, option number 5 again, y1, y2, the guess is close enough, and then it'll give me 0.30308, which is what I had calculated. So solving algebraic questions can be done graphically as well, in this case using point of intersection. Okay, that's probably enough to show you the main outline of today's lesson. So present value was covered. The timeline we will eventually use again, so try to at least work that into some of your questions as you go through this Blackline Master. You've got the input-output or arrow diagram approach if you're struggling with how to solve for the variable using the opposite operations. And then there's the TVM solver, which you can access in class, or you can access probably online as well. Take care.